And welcome back to our foundation engineering class. Uh, we will try to continue the chapter number 5, settlement of shallow foundation. Okay, so today we are going to talk about the settlement based on theory of elasticity. Okay, so we will use the theory of elasticity to estimate the settlement of shallow foundation. Okay, so just uh, to let you know that this part is like a settlement for granular soil. In the previous lesson, we have talked about the elastic settlement of saturated clay, I think. So from here, it will be about this elastic settlement of granular soil. And I hope you remember what is elastic settlement, okay? The elastic settlement is the one that happen fast, okay? So, but this time for granular soil, like sand or gravel. Okay. So, based on the theory of elasticity, how can we estimate the elastic settlement of granular soil? Okay. This is what we are going to see in this lesson. So, we will try to explain how to calculate elastic settlement in granular soil, and the soil will be treated as an elastic material, elastic continuum. Okay. So if we check this figure, we have some definitions here, like df, the depth of footing, h. H here is the thickness of the soil that can settle. And at the bottom of that, sometime we may have rock, okay? So the rock will not uh, shrink, it will not settle. So the settling part soil is this thickness gauge. Okay, and we have the footing dimension, the, the load Q0, the net load. Okay, and we will have also like two type of footing, rigid foundation and flexible foundation. Yeah, and these two parameters, I think you know them already, quotient ratio and uh, elastic modulus, modulus of elasticity. So what is flexible foundation? In flexible foundation, the settlement of flexible foundation is this one. Okay, as the name is indicating, the foundation is flexible. It's not rigid. Okay, so this kind of foundation apply uniform pressure, but the settlement is not uniform. As you can see, the settlement here at the middle here, you have much higher settlement than the edges. Okay, so it is flexible. So it means you push here, this part, the footing even will deform. Okay, that the flexible means the footing can deform easily than a rigid footing. And the other hand, you have rigid foundation, that the settlement can be like this, uniform, but the distribution of the pressure is not uniform. Okay, so we will talk about all these type of foundation, the settlement of all these foundation. Okay, so this section we will first try to estimate the settlement of flexible and surface foundation. That is important. Surface means what? It means the footing is not embedded. Okay, and flexible, you know already. Okay, flexible, the pressure is uniform, but the settlement is not uniform. So here is an example of uh, illustration of different cases of formation you may have. This case, you can see the foundation is the surface foundation. That means the foundation, this footing is not embedded. Okay. See the meaning? It's not embedded. Yeah. And like there is no any existing bedrock beneath like near the footing, near the footing base. So it means like this soil uniform like this. So, and remember this footing is flexible. So the settlement is not uniform. And we may have this kind of condition. And here we have a rigid layer here, like rock, bedrock, laying at a distance, a depth h beneath the footing base. Okay, but still the footing is not embedded. It is surface footing. And in this case, which is the many cases the like the most common case people may have, the footing is embedded. You can see, and we have a layer here, H, embedded at the bottom of the footing. Beneath the footing, we have a rigid layer like rock. Okay, so we will do it for this one first. Flexible footing on surface. Okay, flexible surface foundation on the elastic space. Okay, and then we will extend the equation to this case, this case, when we have a rigid layer beneath the foundation at depth h. And then again, we will extend it to this case where we have the embedment of DF. The footing is embedded. Okay. So we start from uh, we start from the easiest one and we go to the most difficult. Okay. Okay, let's go. So the surface foundation then on the elastic half face, this case, how do we obtain how can we use the theory of elasticity to estimate settlement in this case? Okay, this case is what we are going to work with now. Okay, remember, surface footing. So for this kind of situation, if you have rectangular foundation, flexible rectangular foundation with this dimension P, L, this is the width, this is the length of the footing, on this kind of elastic half base, the settlement under a point on the foundation. Please understand this sentence. Settlement under a point of the foundation is given by this equation. Okay. So in this equation, what do you have and what you don't have? Or can say again, what can you obtain easily and what you cannot obtain? We know what is this one. This I, what is this I? Is what we call influencing factor. So influence factor depending on location of the point of interest on the foundation. That means if you are, for example, on the middle of the foundation, this I, the influence factor is not same. If you are at the edges, it is not same. Okay? So this is maybe the most difficult parameter for us to obtain. And actually all this lesson will be around this I, how to estimate this I. Because the other parameter are easy to obtain, like the net pressure. Okay, that is easy to obtain, this Q0. Remove the weight of the footing, okay? The Q0 net pressure applied by the foundation to the soil. That is easy to obtain, this Q0. B, we know it already, is the width of the foundation, okay? Yeah, we know it already. And what is ES, the modulus of elasticity? Okay, that can be obtained also from the site investigation. Okay, or lab tests are like site investigation phase. You can obtain soil parameter. Okay, chapter number 2, which we show in this program. Yeah, and next we can obtain also easily the Poisson ratio. Sometimes you can just assume it 0.3 or something like that around that. Okay, so you can see, as you can see, all these parameters can be obtained easily except this I. Okay, so what is this I? The influence factor. This influence factor, now let's keep this equation here. Okay, theory, from the theory of elasticity, this is what this is the equation of settlement based on theory of elasticity. Okay, let's keep it here, up here. So how to obtain this I? This is the whole problem. If we solve that, we have solved the whole problem of settlement. Okay, so this is equation proposed by this reference to express the influence factor I for, because as we said, it depends on the position, your point of interest under the under the footing. Okay, this equation is for the point, for the corner of the flexible foundation at the corner. Okay, so you have, remember we are dealing with rectangular foundation. Okay, so rectangular footing at the corner of this rectangular footing, you can obtain the value of I, and replacing it in this equation, you will obtain the settlement at the corner. Okay, for those who don't understand corner, okay, if I take this, for example, check this red rectangle, this point is the corner. Okay, this is not footing, this is just example. Okay, so M prime in this equation, which is the only unknown in this equation, is this one, L divided by B. L, which is the length of the foundation, B, which is the width of the foundation. Okay, so if you have this ratio, replace this ratio in this equation and you will get the value of I, and then you can be able to calculate the settlement on a granular soil based on theory of elasticity. Okay, but remember, this is just at the corner. Okay, but sometimes, as you saw from the beginning, the settlement of a foundation, flexible foundation, is not uniform. Okay, the center of the footing has the highest amount of settlement, so you have to try to get the amount of settlement at the middle of the foundation. So this one is just giving you for the corner. It's not enough. Okay, so uh, for the other location, okay, if you want the settlement at the other, any other location under your foundation, your rectangular foundation, you can divide the foundation in 4 rectangles and use the principle of superposition. So at the beginning of this chapter, I told you that this chapter will use a lot of knowledge from the stress in the ground, the chapter in soil mechanics 1, maybe soil mechanics 1, dealing with stress distribution in the ground. Okay, so if you remember that chapter also, we had something uh, like this kind of thing, estimating using the superposition method. Okay, so what does it mean exactly? Here is an example. For example, if you have this rectangle, okay, like this, and you want a settlement at this point, oh, so what you have to do is